In this video, we shall take a closer look at the applications of calculus in projectile motion. As we have seen earlier, a projectile motion is a motion of an object in a gravitational field. It is indeed a two-dimensional motion, as shown here in this diagram. So in this example, the object starts and lands exactly at the same height. There are other cases. For example, when the takeoff point is higher than the landing point. So in this case, the object takes off here and lands there. Or when the takeoff point is lower than the landing point, like shown here. Like that. In these cases, calculus proves to be a very useful tool in solving such problems. All we have to realize is the application of the following equations. The first one is the way to determine the speed from acceleration. We have seen this equation. It's a general equation. And the second equation is the equation that determines position from the velocity, like that. And in projectile motions, we have to apply these two equations to both the x direction and the y direction. So at the end, we would end up with 4 equations that enable us to solve a given projectile motion problem. Let's see how this works. Let's look at the following example. A man on the roof of a building that is 35 meters tall throws a rock with a velocity of magnitude 50 meters per second at an angle of 35 degrees above the horizontal. Calculate the maximum height above the ground reached by the rock, the velocity of the rock just before it hits the ground, and the horizontal distance from the base of the building to the point where the rock strikes the ground. So what we have here is the following. An object is launched from the top of a building, and it follows this projectile motion and lands on the ground. Of course, we are ignoring the height of the man in this example. The initial velocity has a magnitude of 50 meters per second. This angle from which the object was launched is 35 degrees above the horizontal. This is the height of the building, 35 meters. The first thing is the maximum height reached. So that is the maximum point, and the height is that distance. Let's call it h. We are also interested in the velocity of the rock just before it hits the ground, meaning at the point of impact, the direction of motion is like that. So what is that velocity, meaning magnitude and direction? And finally, the horizontal distance from the base of the building to the point where it strikes the ground. Let's call it r. As we have discussed earlier, the takeoff point and the landing point are not at the same height. So let's write down the equations that describe the motion along the x-axis. So x-axis is that way, y-axis is that way. We start from the acceleration. The acceleration along the x direction is 0. That means the x component of the velocity at any given time is equivalent to the initial velocity's x component. So in this case, it is 50 times cosine 35 degrees. Remember, if the velocity is that way, and the direction above the horizontal is 35 degrees. So that means the x component of that 50 meters per second is 50 cosine 35, and the y component is 50 sine 35 degrees. This follows directly from trigonometry. Now, the x coordinate of this object at any time t. That is given by an integral of that Vx with respect to time. So that Vx with respect to time is a constant, which means the integral would read something like this. This is a constant which can be taken out of the integral sign. And integral of dt is just t plus an integration constant. Let's call it x naught. We know that when t is 0, the x-coordinate of this object is 0. So that means this is 0. So we have obtained two equations already, 1 and 2. Now let's look at equations along the y-axis. So we know the acceleration along the y-axis is acceleration due to gravity minus g, because our positive y-axis is going that way, acceleration is that way, therefore the sign negative there. The y component of the velocity at any time, t, is given by an integral of ay with respect to time. Because ay is a constant, the minus g can be taken out of that integral, and integration of dt will simply give you t plus an integration constant. You can call it u. U is the value of Vy at t equals to 0, and that can be obtained from there. It is the y component of the initial velocity, and we have told you it is 50 sine 35 degrees. Putting everything together, Vy at any time t is minus gt plus 50 sine 35 degrees. So that is the third equation. Now the last equation for how y coordinate changes with respect to time. That is an integral of Vyt with respect to t. Putting everything there inside there, we get the following. So y coordinate as a function of time will be the first one integrated with respect to time is minus g over 2 t squared. That one is 50t sine 35 degrees plus an integration constant. Let's call it y naught. Y naught is the value of y coordinate at t equals to 0. Because the object starting point is there, whose y coordinate is 35, so that means y naught is 35. Namely, it is the height of the building. So let's substitute 35 there. So there we have it, the fourth equation. Now we can solve the problem. First, the maximum height. At the maximum height, that quantity becomes 0. So we need to set Vy equals to 0. If it's not 0 there, then that point would not be the maximum point. So by setting Vy equals to 0 and calculating the time, that is the time it takes for the object to go from the starting point all the way to the maximum point. And you see, equation 3 would give you 50 sine 35 degrees over gravitational acceleration. This is the time. So when t is this, the y coordinate is h. So to determine h, we have to substitute t in the y coordinate right there. So that means the maximum height is given by minus g over 2. Substitute capital T for that little t, 50 over g sine 35 degrees. Don't forget to square. Plus the second term is 50, so that's that term right there. 50 sine 35 degrees over g sine 35 degrees, and don't forget to add the last 35, and that will give you h as 76.9 meters. So that is the maximum height calculated from the ground. So there we have it. The answer for part A, h is 76.9 meters. Now part B, the velocity of the rock just before it hits the ground. So that means here, as it moves like that, what is the velocity? Now it has two components, the x component and the y component. So we have to determine both. We already know what the x component is. The x component does not change at any time it is just 50 cosine 35 degrees. What we need to know is the y component of the velocity when it hits the ground, and that is given by that equation. But in order to use that equation, we need to know the time of impact. In order to get the time of impact, we have to again make use of the y-coordinate equation, because at the point of impact, y-coordinate is 0. So the idea is setting the y-coordinate to 0 and solve the time. Let's call that time t bar. So it's squared plus 50t bar sine 35 degrees plus 35. Now this is a quadratic equation in t bar, so when you solve this quadratic equation, you will get the time of impact. And substituting the time of impact in the second or the third equation, you will get the y component of the velocity at the impact point. Solving this quadratic equation, we get only one positive answer, and that is the answer that counts because we are dealing with time. And it turns out that answer to be 6.88 seconds. Now substituting this in here, we get the y component at the time of impact, and that is minus g 6.88 plus 50 sine 35 degrees, and that is minus 38.8 meter per second. So now the velocity at the time of impact, it's given in a following form: minus 38.8 meter per second j hat plus that, which is 41 I hat meter per second. Now this is just a vector. The magnitude of that velocity is minus 38.8 squared plus 41 squared square root, which is 56.4 meter per second. Now what about direction? Since the object hits the ground like that, and this is Vy, hence negative, and that is Vx, the positive number, we can calculate that angle. And alpha is quite simply arctangent of Vy, which is 38.8, and the magnitude of that Vx, which is 41. And you get 43.4 degrees. So it makes an angle of 43.4 degrees with respect to the ground at impact. So that is the answer for part B. Now part C, the horizontal distance from the base of the building to the point of impact, that means this value for R. So R is just the x-coordinate at the time of impact t bar. And in part B, we have determined what t bar is 6.88 seconds. So substituting that value inside equation 2, you get 50 times 6.88 times cosine 35 degrees, which will give you about 281.8 meters for part C. And that solves the problem. Thank you for watching.